in this recitation class, we talk about mechanisms for SN1, SN2 and E1, E2. Before we start anything, let's talk about what nucleophile. Okay, a nucleophile could be any neutral or anion which is capable of donate electrons to form a new bond. So such organic species are called nucleophiles. For example, neutral nucleophiles like amines, they are neutral, but the lone pair of electrons on the nitrogen, they act as, because of the lone pair of electrons, it act as a nucleophile. Also, any charged nucleophiles which are anionic nucleophile, like hydroxyl, like OH minus, it act as an anionic nucleophile. So either neutral or anion, whenever they try to find any positive charged species, any positive charged species in a molecule, they try to form a new bond by donating a pair of electrons. Based on how nucleophile reacts with the positively charged organic molecule, it divides into two categories. One is addition. For example, if we have any ketone-like molecules, in the ketones, C double bond O is a carbonyl functionality. Oxygens will have partial negative charge and carbons will have partial positive charge. So the nucleophile attacks on the, as we said, nucleophile try to make a bond with a positively charged species. So it attacks on the carbon, and that makes oxygen negative. O minus, a nucleophile. This charged species, upon with any protic solvents or treating with water, it gains hydrogen and it becomes OH. So what you see here, nucleophile attacking on a positively charged organic molecule, but it's just adding, we are just adding nucleophile here. Such kind of reactions are called nucleophilic addition reactions. The second category are substitution reactions. So from the name you can see a nucleophile, when replaces any group, here G represents leaving group. Here also the nucleophile made a new bond, but it certainly replaced a group here which we call the leaving group in these cases. So these kind of reactions we call nucleophilic substitution reactions. In particular, in this video, we're going to talk about substitution of nucleophilic reactions. Based on the way the substitution happens, the substitution reactions are mainly divided into two. One is SN1, other one is SN2. From the name you can see it's called SN1 substitution of nucleophile. One stands for unimolecular. Here SN2, substitution of nucleophile, it's 2 stands for bimolecular. The unimolecular or bimolecular represents how the number of species affecting the rate of the reaction. First we'll talk about SN2 reaction. SN2 stands for substitution of nucleophile and 2 represents bimolecular. And we'll talk about a reaction that's from your experiment. Now I have a reaction here. This is the reaction from your lab. So we're gonna use this today. So I have a bromobutane, which is basically primary alkyl halide, reacting with sodium iodide, NaI. Sodium iodide, NaI, usually it exists in the solution as sodium plus and I minus. So here I minus is a nucleophile and I minus attacks on the carbon with the leaving group. Here bromine is the leaving group. So the nucleophile attacks on the carbon with the leaving group that pushes the leaving group away from the molecule. And we end up with iodine plus NaBr. Okay. So this step is rate determining step. Okay, but if you see the transition state here, when the nucleophile attacking the carbon with the leaving group, so we have iodine on the carbon, so here the dotted lines between carbon and iodine represents formation of new bond. The dotted lines between carbon and bromine it's a breaking of the bond. So the formation of the bond, breaking of the bond happens simultaneously at same time. So this is how a transition state for this reaction looks like. I call this as transition state. And as you guys know, transition states are high energy species, and from the transition state we'll end up getting our product. So from the transition state, in the transition state, both substrate and nucleophile involved. Okay, so that's what our rate determining step is. So the rate of SN2 reaction depends on, if you write the rate law, it depends on concentration of substrate and as well as concentration of nucleophile. Since the rate of such reactions depends on both concentrations of substrate and nucleophile, these kind of reactions is called bimolecular substitution of nucleophilic reactions. From the mechanism, what we need to understand is stereochemistry. Let's see what happens to stereochemistry of any organic molecule which go through SN2 reaction. So I have a molecule here. It's a secondary alkyl halide reacting with NaI. From NaI, as I said, it exists as Na plus and I minus. Now, if we draw the transition state here, CH2, CH3, hydrogen, CH3. There is bromine and iodine. So here, as I said before, the dotted lines represents incomplete bond. The bond between carbon and iodine is formation of new bond, and carbon and bromine, the bond is breaking of the bond. Now, the coming nucleophile is always comes from the backside of the leaving group. Here the leaving group is bromine. It won't attack from the same side of the leaving group. This won't happen. Because if it's coming from the same side of the leaving group, it will have so much of steric hindrance. So rather coming from the same side, it attacks the carbon with the leaving group from the backside. So this is the possible way. So that's why we have iodine, incoming iodine and the leaving group bromine on different sides. So this is how the transition state looks like. Now, the product will be if you assign RS configurations for the substrate and the product, this is R configuration molecule, and your product will be S configuration molecule. Inversion of stereochemistry, that's what we observe in SN2 reactions, which is very important to remember. So we don't attain same stereochemistry. If the carbon, the attacking carbon is R configuration, it becomes S configuration. If the attacking carbon is S configuration, it becomes, after the SN2 reaction, it becomes R configuration. And again, if you write the rate here, rate for this reaction is concentration of substrate and concentration of nucleophile. Nucleophile is sodium iodide and substrate is the starting material. So the rate depends on concentration of both. That's why it is bimolecular substitution of nucleophilic reaction. Less steric factor is more favorable for SN2 reactions. So that brings me to the conclusion of methyl, so the alkyl halides reactivity order for SN2. Methyl alkyl halides are for reactive, then primary and secondary and tertiary alkyl halides. It's a methyl alkyl halides are very reactive and primary alkyl halides, and followed by secondary and tertiary alkyl halides almost shows no SN2 reactions. Now we're gonna talk about SN1 reactions and mechanisms. I'm gonna show you a reaction from your lab, and then I'm gonna show the mechanism. And then we'll talk about the rate, and also is there any effect on the stereochemistry in the SN1 reactions. The mechanism has two steps. In the first step, it's a formation of carbocation. In the very first step, as I said, it's a formation of carbocation. The leaving group cleaves from the carbon. So we lose a bromine and we end up with forming tertiary carbocation. Formation of carbocation is a slow step, and slow steps are rate determining steps. So the rate of the reaction depends on the first step. In the second step, the carbocation reacts with silver nitrate, and the silver nitrate exists as silver plus and NO3 minus. Silver nitrate reacts with the positively charged carbon, because we said like a nucleophile is something reacts with a positively charged species. Rate equals to K time concentration of the substrate. Rate determining steps involves only substrate but not the nucleophile. For that reason, rate of SN1 reaction is only depends on the concentration of substrate. We're going to see one more example reaction of SN1 so that we can see what happens to the stereochemistry in SN1 reactions. As you can see here, I have a alkyl bromo compound with silver nitrate. So according to what we talked, the first step is formation of carbocation, which is rate determining step in SN1 reactions. So we have a positively charged carbon. We form carbocation. Carbocations, they are sp2. Any sp2 carbons are planar. Since the carbocation is planar, the coming nucleophile can attack the carbon from two sides. One from the above the plane and other one from the below the plane. So one from the above the plane gives a different product than one from the attack from the below the plane. So the one is resulted because of NO3 minus attack from the above the plane. So 2 is resulted because NO3 minus is attacked from the below the plane. Now, if you see the stereochemistry of the starting material, it's R in configuration. If you see the stereochemistry of the two products, we have a mixture of R and S. So this will be racemic mixture. The substrate is R configuration. So one of the product retains the same stereochemistry, while the second product will have opposite stereochemistry, which is called inversion in stereochemistry. So let's see how a transition state looks like in SN1. In the first step, formation of carbocation. In the second step, reaction of nucleophile. So there will be two transition states. The first transition state will be when the leaving group leaves. Transition state 1. And the transition state 2 will be when the nucleophile attacks. Transition state 2. SN1 reaction will have two transition states, unlike SN2, because SN2 will have only one transition state. Now we talk about elimination reactions. Elimination reactions are nothing but removing any two substituents from any starting material or substrate. For example, for example, I have a reaction here. This is also from your lab. This is called base catalyzed elimination reaction. Again, it comes under category E2. We'll see the mechanism. So here, the KOH exists as K plus and OH minus. Now OH minus will take one of this hydrogen, and the bond between carbon and hydrogen will move between carbon and carbon to make a new bond, and that process pushes the chlorine away. Here the chlorine is the leaving group. So which ends up CH3 CH double bond C CH3 and CH3. So in this process, the base OH minus is taking a proton from the carbon next to carbon with the leaving group. Okay? The carbon next to carbon with the leaving group loses the hydrogen in these kind of elimination reactions. But if you see here, there are also two carbons with right next to carbon with the leaving group, and they also have hydrogens. So there is high possibility. So there is also possibility of losing these two hydrogens, which results our second product. for example. This is first case, and the second case, if this base takes this hydrogen, it follows the same principle, and that ends up giving the second product. Because more substituted alkenes are stable, this will be your major product. But because of the availability of hydrogens, we also see this product. But this will be your major product. Now I'm going to show the transition state for the E2 reaction, and also I'm going to talk about a stereochemistry factor here. I rewrite the structure here just to see the stereochemistry. Now, when the base comes in here, it takes the hydrogen and the bond forms a double bond, and the leaving group leaves. Now, if you see the hydrogen and chlorine, the stereochemistry is they are antiplanar. So it is so important that two groups are antiplanar. Here we cannot, the base cannot abstract this hydrogen because this is not antiplanar. Only this hydrogen is antiplanar to this chlorine. That's why it only can abstract this hydrogen. If we don't have any hydrogen antiplanar to the leaving group, probably we don't see the product. So in the E2 reactions, the two leaving group is supposed to be antiplanar to each other. Okay, I have a reaction here on the board. When you have a strong base, the leaving group bromine here, and we only lose hydrogen on the carbon on the left side, but not on the right side, because the hydrogen is antiplanar to this bromine. If you see the hydrogen on the right side, it's not antiplanar, it's on the same side. So the two leaving groups are supposed to be antiplanar to each other. So the base would take this hydrogen and it forms a double bond and the bromine leaves. So the product will be this will be your major product. So this is how the stereochemistry helped to predict the major product in the reactions. Now we talk about E1 elimination reactions. This is also a reaction from your lab, example for E1 reaction, and this is called acid catalyzed elimination reaction, since the elimination reaction is initiated by sulfuric acid that we add to the substrate. whenever we add acids like sulfuric acid to alcohols, the OH group, the alcohol, get protonated first. So this becomes H plus. The oxygen takes a hydrogen and becomes H2O plus water molecule. Now here, OH, the hydroxy groups are not good leaving groups, but the water molecules are really good leaving groups. So we see the formation of carbocation, and this is rate determining step. Since the rate determining step depends on the concentration of the only substrate but not any base or acid in this case, that's why this is called unimolecular elimination reaction, E1. Now we have a carbocation formed. In the second step, these three carbons have equal chance to lose a hydrogen to form an alkene. These are the two alkenes we end up making in the E1 reaction. These two are the rate equations for E2 and E1 reactions. And the E2 rate depends on the substrate concentration and the base that we used. And the E1 reaction, the rate only depends on the substrate because the substrate only involved in the formation of carbocation, which is rate determining step.